Okay, hopefully everyone's had a chance to get some more coffee, maybe a little bit of food. So what we're going to walk through now, and this will be hopefully pretty hands-on. So if you've got a laptop, hopefully, has everybody found the stuff on the web page? Hopefully the data set is up there, the spdata2.csv. There's also an R Markdown and a Python Jupyter Notebook. Whichever of those two languages you prefer, I'm going to walk through both of them up here, kind of explain what's happening inside of them. But if you want that available, go ahead. Paul, go ahead.
There's a question from the chat. When you get a chance, could you talk about the difference between a parameter and a hyperparameter?
Yes, we will get to that. That was a fantastic question.
You can just pull up our website. I can help you do it.
Sure. Yeah, no, I should have brought it up here. That makes way more sense.
So PDHP. So if you go here to workshops, this is pdhp.isr.umich.edu. Hopefully we can display that for you.
It's not making this top part zoom in. Whoops.
And then if you go to workshops tab, oops. And then within this page, there's a workshop video materials page, and everything's here. Thank you.
Okay, and if you're a Python user but don't necessarily have Jupyter Notebooks installed, I think if you download the zip file, there's also HTML versions of everything in there that you can load all the code and its output in your browser, so you can copy and paste and stuff from there. Over here?
Just up one section, right there.
Oh, the precompiled version. Yes. So like if you click on Python version here, yep. So here's everything. So you can copy and paste the code as we go along into whatever way you like working with Python. And the same thing for the R. If you're not an R Markdown user, feel free to copy and paste from the sort of the darker grade boxes, the code. We've just got all the output here to refer to as well. So. Okay. Any questions or anything before we get started? Ben. Okay, so I've mentioned before, our illustrative example that we're going to use for this is predicting whether or not someone is going to respond to an invitation for a survey or an interview. So our experience is going to be data we collected from a previous survey that we hope generalizes to future surveys. So hopefully people don't respond or do respond for the same reasons, so this is a good predictor for another survey. Our performance here, most of the time we're going to look at the correctness of our predictions. So as we're working through the code, we'll see how many times we guessed the right thing. And I chose this example because there's actually a companion special issue of the Survey Practice Journal that corresponds to this particular task and data set we're going to be using. So if anyone's interested, they can follow the link here. It was a special issue that Trent Buskirk, Antje Kirchner, Kurt Signorino, and myself put together, walking through different machine learning methods for survey research. So Trent has a great article that looks at decision trees and random forests. I had one on neural nets. Antje and Kurt had lasso and SVMs. And so if you want more information than we're going to be talking about today, there's sort of a companion there you can look at stuff. So I wanted these to kind of be linked together so there were more resources for everything. Okay. So with that in mind, the way the data is organized, the particular attributes we're going to look at, we've got the age of the respondents, whether or not they own a cell phone, their education level, gender, income, landline, and region. For purposes of this particular data set, I will acknowledge that the gender variable is binary. That's the data we had available. To get more accurate predictions, we might want to sort of reflect the actual spectrum of genders out there in the real world. But for this data set, that's sort of the limitation we're working with. We're also making the assumption that we know all this information in advance about our potential survey people versus waiting for them to provide this later. So maybe that means that we estimated it for different households using information we purchased from different vendors, or lots of different ways of getting that in the first place. Okay. And then the outcomes, I'm going to try to use that word from now on. The outcomes we have here are whether or not they're a respondent or a non-respondent. Okay. Questions about the data set? Great. So, the process of machine learning has kind of 6 big steps to it. We'll walk through each one of those here. So the first step we always start with is collecting our data in the first place. This is exactly like any other kind of analysis we're going to do. We need data to work with. And of course, this is where a lot of the work actually happens, is finding this data, collecting it, building it in the first place. For today's workshop, we're just going to assume that's already done using the CSV file that's available for download. The second thing we do, and this is where also a lot of work happens that isn't talked about. So it turns out that in the machine learning pipeline, like 90% of our time is spent over here, versus the last little bits are the fun parts of actually building the model and then seeing how it's doing. So people don't talk about these things as much, but we're going to walk through how they work today. So basically, this is just our data cleaning step. Just like any other data analysis, also the data linkage problem, how do we take 2 data sets and merge them and make sure it worked and all that kind of stuff. All that happens in machine learning just like it does everywhere else. So what are some common data preprocessing steps? I guess first, let's talk with a neighbor to kind of get back in the groove of things. What are some possible challenges? So we have a whole bunch of data we collected. What might make it difficult to feed into machine learning? What are some problems that could arise that we need to handle to get it ready for analysis in the first place? Think for a minute, and then talk with a neighbor, and then we'll come back together. Okay, sounds like conversation's getting kind of quiet, so let's go ahead and come back together. What are some challenges people talked about? What can make learning hard? Yeah. Okay. Other thoughts people had? Yeah. Values. Yeah, it's not always possible to collect every single attribute for every single instance, so we're going to have some gaps. Other things that could go wrong or make things difficult. Yeah.
Maybe population changes, what you're doing now, and then next month population shifts a little bit, so you're not as accurate.
Yeah. So there are, in machine learning, in data mining language, we would talk about these as concept shifts and concept drifts. I think it sounds like it's similar in population language. The idea that the population is changing over time. The thing we're trying to measure, old data might not reflect the current present state. So it could be the case that people are not responding for different reasons. If we collected this data back in the 70s, it would be more that people, when phone interviews were just starting, people were more likely to at least answer the door if somebody came, but they might not pick up the phone. Now it's even harder to even just knock on someone's door and talk to them. Those kinds of changes. That's drift. Shift happens when there's an abrupt change. So the data is just suddenly completely not, the underlying patterns that are causing the attributes to lead to the outcomes are completely different due to some event in the world or something like that. So that's definitely something that could happen. On the unsupervised learning side, one thing that we might do is try to identify when drift and shift are happening as well. So how are our attribute values changing over time and stuff? Great example. Yeah.
Issues of measurement, like how granular the measures were, and also like if you have continuous variables like income and age and education, you're going to use them as continuous variables in your prediction model or as categorical.
Yeah. Great. Related to measurement, we could also just have measurement errors, so we can have noise.
Yeah, from the chat we have non-normal data, outliers, and we have a few coming in now. Class imbalance.
Okay.
Very rare attributes, and high correlation among collected measures.
Those are all fantastic. Okay. We'll hit on a few of them in a minute. Yeah.
Actually, I'm wondering if you can speak a little bit more to the non-normal data and how big of an issue is that within these algorithms?
Yeah. So In some ways, it's a bigger issue in classical statistical methods because we assume underlying distributions for the method that we're using. When we use decision trees and random forests and even neural networks for the most part, we're not assuming that the data comes from any particular distribution. So in some ways, machine learning is actually a better fit if the data isn't normal because we don't have to test for what sort of distribution it comes from and make assumptions there. It's just going to try to pick up on patterns regardless of the distribution. That does mean that we're neglecting some information that could be useful. There's definitely benefits in statistical methods of knowing that this comes from a normal distribution and how we analyze it and things. But we're going to typically not make those assumptions ahead of time. Great question. Some of these other ones are things that we classically see in analysis that also matter here too. Okay, we'll talk about a few of these in more detail. But what I really like about this is that we had a really long list. This shows that in general, the data we collect is difficult to work with. It's often messy, we're missing stuff, there's noise, errors, etc. What we didn't quite mention was irrelevant information. So there was the idea that attributes might be correlated to each other. That can be a problem, but also attributes just might not be relevant to the prediction problem we're working with. If I collected what color someone's house was, probably doesn't have a lot to do with whether or not they're going to respond or not to my survey, but it is a piece of information I could collect if I wanted to. And then this idea of different types of attributes, continuous versus categorical and stuff too. Okay. The problem we face is, given this challenge, how do we make our data workable for our machine learning methods? What kinds of things do we need to do to prepare it so that it's useful? Implication is that if we do this data preprocessing step, we're going to get at least slightly, oftentimes even better performance than otherwise. So it's beneficial to spend some time on the front end cleaning up the data set so that we get better results later on. It'll make it easier to learn. So I've got a list of common preprocessing steps here. This isn't exhaustive. There's other ones, especially some that were mentioned in the list that I'll share that text file with everyone afterwards. But this is commonly ones that we do. The first step is we're going to convert our data set to a wide format. So the more I worked in social science, the more I learned that some people use wide formats, some people use long formats for everything. Long formats where we have sort of one row for every attribute value instance combination. Wide is when it's one instance is an entire row. So long format does have its uses when we're trying to make predictions over time. Each time point could be a separate observation in a long format, but most of the time we're going to do wide. We want all the attributes together for an instance at once. This also might mean that we're merging data sets, as we've talked about too. Our attributes could be spread across different files that we've collected over time. We need to be able to merge those so that we have all the attributes for an instance at once. We can't really proceed until for every instance we have all of its attribute values. We talked a second ago that maybe outliers are a problem. It's not uncommon to remove them here because they can skew our predictions one way or the other. Test it with and without and see what the differences are. They could be due to measurement error, they could be bad collection, etc. One of the places this came up for me, I was doing, when I was first getting involved with survey research, I was building these machine learning models that would predict whether or not someone was going to finish a survey. So we were collecting information about how long they were spending on each page of a web survey, what order they were answering questions in, and then on the fly predicting, are they going to get to the end or not? And we had a lot of measurement errors where just trying to track things like how much time someone has spent, we got a bunch of negative times and a bunch of times that are between now and the end of the universe, and some other really crazy values. And so these things tend to happen. We also need to handle missing data, and it depends on the machine learning method we're using for that. When we talk about neural networks later, they can't handle missing data, so we have to do that as a preprocessing step. If we're doing decision trees and random forests, then we can skip this and let the method handle it for us. But the idea is that missingness can affect our predictions. Different ways of handling it, we could just throw out the instances that have missing values. That, of course, causes problems if we don't have a lot of instances to start with. Maybe we try to impute values. Maybe we take the median or the mean. Or we even build a whole other machine learning model that learns how to predict the value of an attribute based on other ones that it sees. So we're changing what the label is, etc. Different ways of handling that. The two we'll talk about in code today are how to handle different kinds of attributes. So if we have numeric attributes, we might want to normalize those so they all have similar ranges to each other. And if we have categorical attributes, we might need to convert those into dummy variables so that we can make use of them with numerical methods. So neural networks are going to try to multiply all of the time and then add a bunch of stuff. And we can't multiply a number times the color red or times male. And so we need to have things as numbers inside of here. In machine learning, we call this one-hot encodings. When we convert a categorical into numbers, it's basically the same idea as creating dummy variables, etc. that we've probably seen before. Questions about preprocessing so far? And then we'll look at some code to handle the last two. Question?
Give an example of a one-hot categorical.
Yes, I will have one in a couple slides. Great question. Another question.
Do you always normalize all the attributes?
You don't have to. So it depends on how far spread apart they are. If I have some where I have, like, if my same data set has age and someone's BMI and their income, and I'm treating income as a number rather than a category, then these are very different ranges to each other, and it improves learning if we collapse them so they're more similar to each other. We don't have to. We can treat them like they were originally. You might just not get quite as high of accuracy and stuff. And so, but if all the numbers had similar ranges to start with, then we might not have to go through this. Sort of depends on the data set. Question?
Regression analysis, or is the different?
The more data we have to learn from, the better. Especially the biggest challenge in machine learning is when you start to get to the point where you have more, just like in statistics, if you have more attributes than you do instances, you're definitely not going to be able to learn too much. So the more data, the better. Different machine learning methods handle small amounts of data better than other ones, just kind of depends on what we're working with. But it is definitely a challenge. It's a little bit harder to do like a power analysis where we say we need this amount of data to get this amount of statistical power at the end, but some of those are still useful techniques for trying to come up with the right data in the first place. Question?
Just a request from the chat is, could you please repeat the questions?
Oh yeah, I will definitely do
They're having
that.
trouble hearing.
Sure.
There are mics, so they should be able to hear, but they're not always. So if you wouldn't mind just repeating.
Yeah, so that last question was, do we think about data set size in the same way here as we do in statistical methods, or sample sizes and things? The previous question was whether or not I can show an example of one-hot encoding, which I will do in a second. Cool. Okay. Any others? Yeah.
I might have missed it, but
It's okay.
like age, BMI, and income, they have different scales.
Uh-huh.
Do you scale them individually? Like
Yes.
you're in this say age, you know, you get a specific scale them and then this for BMI.
Yes, yeah, we tend to scale them within attributes. Yes. Because the idea was we want each attribute to have similar ranges of values. So how do we do that? Oh, question.
Sorry, one more.
Oh, it's okay.
For selecting potential attributes, is it better to cast a wide net, or is it better to pre-select based on theory?
We will come to that question in just a minute. That was another great one. Okay. So, we've got a numeric attribute. We've got several numeric attributes. We want to make them in similar ranges to each other so we can learn a little bit better. So it's not that one is dominating the predictions compared to the other. The two common ways of doing this, one of them is just to convert it into every attribute into a number between 0 and 1, where 0 represents the minimum value, 1 represents it's the maximum value. So this is useful whenever our attributes, its contribution to our prediction might depend on where it falls along the whole spectrum of possible values. So to do that, we just take the old value, subtract off the minimum, and divide by the max minus the min. So if we do that, the largest values are going to be close to 1 because they're close to the max. The smallest ones are going to be close to 0. An alternative would be to compute a z-score. So this does maybe assume that the data kind of falls from a normal distribution, but not necessarily. But this is more useful if what matters for the prediction is how many standard deviations away it is from the average. So this is where it falls in the total spectrum. This is how far it is away from the mean. So similar ideas, but maybe slightly different information. So we've maybe seen this before, but to convert something to a z-score, we just take the old value, subtract off the average of that particular attribute, and divide by the standard deviation of the attribute. Again, negative values here are going to be things that are less than the mean. The more negative it is, the more of an outlier it is. The larger the value, it's bigger than the mean, and if it gets too big, it's maybe an outlier as well. This could also be used for outlier detection too. We could throw away instances where the z-score is too high because it's just too many standard deviations away. Let's look at that in code. Okay, so what's the best way to show this? Everybody, that doesn't help. Oops, if I remove this. Okay, can we read okay in the back? We're good? Okay, so we'll walk through R first, and then we'll do Python. But this is, again, just some details at the beginning. This is what our workshop is. The code first for reading in the entire data set. So we just do, it's a CSV file, so we would do read.csv, save it in a data frame, just our way of representing the table. And here we're just going to print out the first 6 instances so we see what it looks like to start with. So this original data set has way more than just the 7 attributes that I mentioned before. So if you want to be trying other combinations of these in this prediction problem, you're more than welcome to use some of the others as well. But when we pre-process, we're going to take and focus on just those 7 that I mentioned before, so it's a smaller problem and a little bit easier to work with. Again, block of code for reading and seeing it. Then we get to the processing stuff. So we'll be using, I think a little bit later down, we'll be using Caret to do a little bit of this pre-processing stuff for us. So we're just going to load it from the top. And what we're going to do is, we've got all data is our original information. We're going to make a new data frame, or kind of a spreadsheet, that represents the data we're going to be working with for the machine learning. So as we process it, we're going to add it to this other data frame. So I'm going to start it by looking at just the label information, the outcome that we're trying to predict. I don't remember to use outcome. So in this data set, new respond 20 was what we had called whether our simulated, do they respond or not to the survey. So we're going to grab that column, we're going to turn it into a data frame, and we're going to call that column processed. When we're here, this just means we have a spreadsheet with one column, which is our outcome of response for every single respondent. So we've got all the right number of rows. We're going to start with just the outcome. Then we're going to normalize the age variable. So I can take my original age information, subtract off the min, divide by the biggest minus the smallest. In this line of code, we'll create a new set of age values that are all in that 0 to 1 range, following the same formula as the slide. If I wanted to do the z-score instead, I could uncomment this line and use it instead. So again, I'm going to take the original age value, subtract off the average, and divide by the standard deviation. We don't necessarily have to build up 2 different data frames. I just like to, so I always have the original value around in case I need to make use of it later on. But we could have done this in place. I could have said all data age is this stuff over here. And it would just copy over the top. And the reason for this is we think it might be more informative about where it falls along the spectrum as opposed to how far it is away from the mean. And we do this, if we had a whole bunch of numeric attributes, we'd want them to be similar to each other so that one doesn't dominate the predictions over the other. If I do the same thing in Python, can everybody still read this code okay in the back? Pretty visible? Okay, fantastic. Okay, so again, comments at the top just describing what we're doing. But we're going to have a pretty similar process for reading everything into Python as we did in R. So in particular, we're going to use pandas as our data management library. There's lots of different ways of reading data into different programming languages. Pandas is great because it essentially builds data frames that are just like R, or very similar to R. So this will make it easier to kind of keep our 2 running examples similar to each other. So we're just going to read in that particular CSV file. Again, we can see the first few instances. It's going to be the same as it was in the other one. And here, we're going to separate out the attributes we're most interested in first, just to make the rest of the code a little bit easier to work with. So I can take my original data set, and I put 2 square brackets to say that I'm working with columns or attributes. I list the ones that I want, and now filtered is a new copy of the first one that only has those particular attributes. So this is the information we're going to use to generate the stuff we're going to use for machine learning. And I've thrown away the other ones for now. If you wanted to, again, change this where you're working with other ones, feel free to add any other columns inside of here. Just comma separate them, and then we'll still have them available here, and you can pre-process them however you like. This is how we read in a data set, and then choose which attributes we're interested in. Then we can filter them. One slight difference between what we're going to be doing in R and what we're going to be doing in Python is that the machine learning libraries in Python prefer it if the label is its own thing, separate from all the attributes. So we're essentially going to have one table or spreadsheet that has all of our attributes in it, and the label is just going to be a list next to that. It's still going to be matching so that the first thing in the labels is the correct outcome for the first instance in the attributes and stuff, but they're just going to be in 2 different variables. We're going to use labels as our variable for the outcomes, and we're going to use processed, again, like we did in R, where that's going to be the attributes we're interested in. Okay. So all this means here is take this data set and drop off the new respond 20 column. Anytime we want to remove a column from something, we just call .drop. And the axis equals 1 means to do this at the column level instead of the row level. So we're throwing away attributes instead of instances. If I wanted to drop particular instances, I would pass in which one's here, and axis would be 0. Okay. So now we have this thing without this column. Then again, we're going to find the minimum and the maximum of the age so that we can normalize it by taking the old value minus the min divided by the max minus the. So really similar code to what we had in R, just a little bit different syntax. Questions about one or the other? Again, if I wanted to do a z-score instead, I have the code for that right here. So it's actually nice. Z-score is a thing that exists inside SciPy. And so I could just tell it to do this thing to that column, and it will convert the whole thing to a z-score. There's other things we can pass into apply that make it do other stuff too. So it might be worth exploring sometime if you're interested. Okay. And then I'm going to drop the old age and replace it with the normalized version. Is all this line of code here is doing. Let me make that go up. Take the data set, remove age, replace it with this one. And again, axis is 1 because we're dealing with columns or attributes here. So I guess that's another difference. Here we're changing everything in place. In the R, we're building it up column by column. Any questions? Okay, let's talk about categorical variables. So why do we need to treat categorical variables special? Because most of the machine learning methods we use are going to assume that attributes have an ordinal relationship, that one thing is bigger than another or one thing is smaller than another. And that naturally happens for the numbers, but it doesn't always happen for things like red versus white versus blue, or if we have states as one of our categories and stuff. So what we're going to do is we need to convert these so that the machine learning method can use it. And we're going to do that by making new separate attributes for each value of the original one. So again, if I'm doing the different states, I'm going to end up with one attribute for each state, as opposed to state being a single attribute. The downside is this does make our data set a lot wider. We're going to have more attributes now, but it's going to make it easier to learn using each one of those. If you've ever made reference category, we do this all the time in the linear and logistic regression as well. We make dummy variables when we have different categories. It's basically the same process here. And we'll also even have a reference category like we would there. So if we're trying to predict how much more money a person makes in one state versus another, we would pick one of those states to be our reference category, and then we'd have all these indicator variables saying whether or not, which of the other states a person lives in. So indicator variables is another way of looking at this. Question?
Does this mean that instead of having like color red or blue, you have red, yes, no, blue, yes, no? Okay.
Exactly right. So here's the color example. So we're going to take our original color, could have been red, white, or blue. So yeah, now we're going to have a color red, a color white, or color blue. That was a great lead-in. Thank you. So anytime it was a red, we're going to have color red be 1 and the other ones be 0. If it was color white, then white is 1 and the others are 0. And if it was blue, then blue is 1 and the others are 0. So we can see that we did have one attribute or column before, and now it's 3 times as many because there were 3 possible categories. Again, it's states. You would have one that's, if it's Michigan, the state Michigan attribute would be a 1 and all the others would be 0, etc. Now we'd have 50 new ones instead of 3. Question?
Is that like a label that I create? Like, let's say I have the variable age and I create ranges and then I have a label for each range? Like,
Yeah, that's a fantastic question. So if you have like a numeric or a continuous variable and I create categories or groups of it, with age, those would have an ordinal relationship. So like 18 to 25 is less than 26 to 35, etc. And so for if that's how we categorize them, then we probably don't have to go through this step in the first place. We could simply say that the smallest category is a 0, the next category is a 1, after that it's a 2, which is how we do income groups in the data set that we're looking at here. So the lowest income group is, I think, a 1, the second next income group is a 2, etc. So when we build those categories, if they have an ordinal relationship, we can say that one is bigger than another one, then we don't have to go through the trouble of building all these extra categories. We can treat those as numbers. We just assign a number to each group, an increasing number as it gets bigger and bigger. Here, there's no way to say that white is bigger than red or less than blue or anything like that, and so we have to treat them as separate categories. Just like with states, maybe we would want to say that Michigan is more than Ohio, but not necessarily. Question?
2 questions. I'll give them to you one at a time. Why is this referred to as one-hot encoding?
Sure. So it is the 1 of one-hot comes from the fact that only one of these things is a 1 and the rest are all zeros. It's an encoding because we changed the name. I'm not sure where the hot part comes from. Yeah.
Okay, and the next question. If you have a continuous measure that you have clumping, for example, a bimodal distribution, is it better to make it categorical for each clump, or each mode of the distribution?
Ooh, that's a really good question. Suppose it would depend on how the 2 different clumps lead to the prediction. Like if it's relevant to know that one clump had a higher value than the other one, then we might keep it as a ordinal 0, 1. Or say even if we had like a triangle, because then we'd have more than 2 categories. So if you had a small clump, a medium clump, and a big clump in terms of a value across this, which isn't helpful for hopefully people can see that. Then you might want to say 0, 1, and 2 if it's relevant that this first mode was smaller than the other 2. If it doesn't matter the order of those modes, then we would treat them as a categorical like this. Really good question. Okay. Any others? Yeah.
When we do dump coding, we usually have a baseline or default category, and it's 0, 0, 0.
Yeah.
Okay.
So,
Thank you.
yeah, great question. So what the trouble here is that these are all correlated to each other. There's extra information that we don't really need. If I know that red and white are both 0, then that must mean that blue is the color. So what that means is I can actually throw away the last category. And so I would only have color red and color white. And so when it's a 0, 0, that means it's the one that I wrote. This is my reference category, essentially. You don't have to do that. You can use this original method. We tend to get slightly better performance when we drop one of them. And it doesn't have to be the last one. It could be the first one. It could be any one that you want to make the reference category. I typically do the last one just because code-wise that's a little bit easier, but you're welcome to use whichever one you want to be. In statistics, we call this the dummy variable trap, where if you include all of them, it can hurt your performance a little bit. Again, we're going to make dummy variables or indicator variables for each, drop one of them because it's redundant information. Question?
You won't have in this case
Two,
parameters,
exactly.
right? And then 0, 0 will correspond to color.
Yep, exactly right. And so if I was doing states, then I would have 49 instead of 50. It's not a lot of savings, but it's a little bit. And then whatever our last state is, that would be the all zeros. So looking at any other questions about the technique? Code-wise. We did a little bit more stuff here. Okay, so we can do this slightly, that doesn't help. In terms of how I wrote this in R and Python, I do it slightly differently if the variable had 2 categories or if it had 3 or more. Because anytime it has 2 categories, we can just call one of them our reference and set it to 0 and make the other one a 1. So I just pick the first value each time to be the 0 and the second value to be the 1. So if I'm doing, here we go. And male, and what I'm taking advantage of in the code here is the fact that when R read all this in, it turned it into factors. Factors are how it represents categorical information. And so it's going to assign indices or numbers to each one of those categories. The first category is a 1, the second category is a 2, etc. And so if I want to make the first category a 0, I just take whatever number that category is and subtract 1 from it. The same thing, the second category then becomes a 1. So anytime you have a factor with 2 things, meaning an attribute that has 2 categories, we can just use this little piece of code to convert it to a 0, 1. So it's the same as doing the 1 hot, but just in one step. Okay. We're going to do something kind of similar here, where in the original data set, we had this telstat variable that said what kind of phone they had. So in that, it was the first category was they only have a landline. The second category is that they have both a landline and a cell phone. And the third category is that they only have a cell phone. So if I'm looking at that, and I want to know 0 means no landline, and 1 means they do, then I check to see, was the category 1 or 2? If it was, then they have a cell phone. So this thing is going to be true, and turning true into a number makes it a 1. And if they didn't have, if it was category 3, then both of these would be false. And so this whole thing is false, and turning that into a number makes it a 0. So lots of ways of writing this particular part. I just did one that sort of works in one. Hopefully that kind of makes sense. We do the same thing for cell phone. They have a cell phone if they're in the cell phone only category or the cell phone and landline category. And that's how we know which one they have. So these 2 attributes weren't in the original data set. We had to pull that out of another. Okay, cool. So then we've got the education level. So that one we can keep ordinals. This was the idea of making categories of ages as well. So here we've got 3 possible categories, whether they have a high school education or below, if they've had some college, or if they have a college degree. And in terms of the amount of education someone has received, this is less than this one, is less than this one. So if we think that the relevant information for our prediction is how much education someone has, there's an ordinal relationship there, and I can just make these numbers. So this is category 1, category 2, category 3. If I then subtract 1 from that, in my data set, I'm going to have 0 means high school or below, 1 is some college, 2 means that they have a college degree. That was basically the step that already happened ahead of time for the income variable. So in this original data set, they had groups of income categories. The lowest amount was the smallest, etc. In terms of making one-hot encodings, this is where we used caret. So caret has this dummy vars function that we can pass in a particular variable, and it will do the one-hot encoding for us. So here in this data set, what region somebody lives in. So there's 4 possible. There's Northeast, South, Midwest, and West. These ones here. And so this is going to then convert that into a one-hot for us. We don't have to do any of that processing ourselves. So I just call dummy vars and say which variable to convert with a tilde in front of it. I'm then going to convert that into a data frame, and then I'm going to assign the names to the new categories, the new attributes. The first one was a 1 whenever it was a Northeast region. The second one was a 1 whenever it was Midwest, etc. So this code works regardless of how many categories you have. If you had states as well, then I would just do tilde state, and then I would have to come up with my list of states here. But it would work regardless of the number of possible categories. I could have instead done it by hand, like this, where Northeast is a 1 whenever the region was Northeast. Midwest was a 1 whenever Midwest was the region, etc. This code will do the same thing, but in this case, I have to specify 1 line for every possible value, versus, again, this one is the generic one. Once I have those one-hots, this is where I'm dropping the last column. So anytime I have a data frame, it wants to know which rows first and then which columns. By putting nothing for the rows, it means use them all. And then this just says go from 1 to all but the last one. That drops our category. And cbind just takes 2 data frames or data sets or spreadsheets and pastes them together sideways. So this is going to take all the columns in here and add it to the end of all the columns. That's all of our pre-processing. I can then call head on it to show me the first 6. So again, in R, we kept around our outcome. We see our age is different than it was before, and we've got a bunch of, here's our one-hots for the region. We've got our education changed. We've got our new landline and cell phone variables. Hopefully the example in here, you can translate this to other problems that you're working on too. So if you have a different data set, the same strategy for converting things to one-hots, et cetera, will work as well. Questions about the R example? Okay, I'll try to do this faster in Python. We do it a little bit different. Okay, so when we make the dummy variables, we're going to actually loop over all of the instances and see what the right value was. So when I call filter gender.values, this is going to be all the values of the gender attribute. I'm going to look at it and see, okay, if it was female, we're going to say that the code is 1, otherwise it's a 0. And we're just going to add all those into a list. This is a similar, we can't do this in one line like we did it's uglier to do this in one line than it was in R. So here's a little step-by-step what we're doing to build up that particular variable. And then again, we're going to drop the old gender column and then add the new. And the same thing for landline and cell phone. We look at each value. If they had both, then that means they have a cell phone and a landline. If they were cell phone only, CPO, cell is 0 and land is cell is 1, land is 0. Otherwise, the other categories they had a landline. So we can add that. Do something similar to find our education level that we did before. The relevant thing here is that once again, we've got something that builds dummy variables for us. So in pandas, it's get dummies. You pass in a particular attribute, and it will then create dummy variables for us. So this thing has all the one-hot encoding for this particular attribute. We give it some column names. We drop the last one, and then we add it into our data set. And if you had a different column you wanted to do one-hot encoding for, we would just change the name being passed in here because this is the particular column. We would change what the possible values of it are, and then the same formula works, the same recipe. Okay, enough pre-processing? Okay, so the next step we would do after we have our data formatted in a cleaner way that'll work with machine learning is we might want to throw out attributes that aren't going to be helpful for us. This was a question from the chat earlier. So the question originally was, is it better to collect too much and then handle that later, or be a little bit more targeted, I think, in the information we gather? I think that was pretty similar. So let's talk about that in groups for a second, because I've been talking for a little while. So let's think about sort of what would happen if we collected too much information. What could go wrong? Or at least why might that be a bad thing? And then we'll come back together. Feel free to get up and walk around a little bit while we're talking, grab some more coffee, etc. We'll take another break in a little while. Okay, so what are some possible situations where we might have too much data? Or when might that be a problem? Any thoughts we had in general about too much data being an issue? Too much data sounds like a good thing. Yeah.
I guess if you're training your model on, when you're testing it, like your model has memorized the data,
Sure.
and actually learned anything.
We will definitely come back to that one. But yeah, if we talked about this a little bit before, when we evaluate our machine learning model, we want it to be on data it didn't see already so that we know that it's generalizing to something new. Fantastic point. Other thoughts? Yeah.
Repeating or following the noise of the data.
Okay. I like overthinking. So in what ways might it overthink? I really like this idea.
I mean, if the training set that we are using have like noise or have like trends, particularly from that training set, then when I'm using in the testing set, it might not perform that well because it's following the noise of the training data.
Okay. We'll talk about this in machine learning. We call this overfitting, which probably comes from statistics as well. The idea that there are differences between the data we use for learning and the data we eventually evaluate it on, where it might learn to do really, really, really well on the learning data, but it might learn nuances that aren't generalizable, that they're true only of the learning data, and then not do well over here. That's a great example. I like overthinking for that. That makes me happy. Yeah.
So the question's about like collecting too much data, so you can always just like ignore the data that you don't think is relevant. But if you're collecting from, say, like human respondents, you just might get poor quality data in the very
Sure. Yeah, so lots of reasons from sociology and psychology why this might happen. But if we ask people for too much, the data quality tends to go down over time. They start straight lining or speeding and some of the other things I talked about before. That's a great point. Yeah.
Yeah, this is a little similar to the overthinking, but the models could get too confident in the conclusions and not be able to deal with new situations.
Cool. That up here with this one. I think there was another hand over here. Yeah, go ahead.
It can take a long time to crunch all your data.
Sure. Yeah, especially some of these methods are going to take a little bit longer than running like a linear or logistic regression. So the more data we feed them, the longer it's going to take for them to spit something out, which isn't so bad once you know you've got like the right attributes and the right model. But when you're debugging your code and trying to figure out what's going on, that gets really, really frustrating. There's been plenty of times where I've pushed a button and come back the next morning because that's how long it took to run a model and be like, oh no, I left something out. And then I have to do the whole process over. That is definitely an issue too. Okay. These are all really good points. So, question
From the chat.
Yes, thank you.
Cursive dimensionality.
Yes.
That's 1. 2, issue of correlation. 3, memory constraints.
Ooh.
Those are 3 for your list.
Okay, so it takes longer correlations between attributes and memory concerns. Yeah, we can only store so much data in the computer at once for it to be thinking about. And to be able to do too much data, I might need like a server or something. Awesome.
We actually have a question then as well.
Sure.
On the overthinking point, can't we do the train/validate/test split on the overall data set?
Yes, which is what we're going to talk about soon. Great point. Okay. So these are all really good reasons why too much data might be an issue. Okay. So the particular issue we're going to talk about here is having too many attributes. So in general, having more and more observations or instances is a good thing because it's more examples to learn from. But the bigger problems tend to happen where we've over-collected too many measurements about the world. So this could happen for a few different reasons. The correlation one is one example where if a lot of my attributes are correlated to each other, they all share the same information. So they're not necessarily helping with the predictions differently from each other, and we might pick up on too many nuances that are going on there. The other issue is that sometimes we just collect things that don't matter at all. We do tend to collect more stuff than needed. We're better safe than sorry. I'm not advocating for collecting less information in the first place, because hopefully we can weed out some of those things later. We don't necessarily know in advance which things are going to be good predictors, what the best attributes are. So my personal practice is to just collect stuff and then prune down later. One particular issue that we'll talk about here, more than the correlation is especially problematic in statistical methods. They tend to be a little less problematic in machine learning. They can crop up and be issues. A little bit bigger problem is whether or not we have attributes that don't matter in the first place. We call those irrelevant attributes. So the idea here is that having all these irrelevant ones not only increases the amount of time it takes to run, like somebody mentioned, but it might discover patterns that don't really exist. So how many people have heard the term spurious correlations before? Yeah, most people. Let's look at a couple of those. The idea here being that two things look like they're closely related to each other when it's just pure random chance that it happens. Because there's so many possible ways things can be combined. Hold down, here we go. So there's again, I need to exit out of my slideshow. There's an entire book on spurious correlations and a website devoted to that too that gives a lot of examples of this. The two things that might have been related to each other, the amount of money that arcades earn and the number of PhDs in computer science. You can think maybe there's a relationship there. Most CS people tend to like games and technology and stuff. So as CS gets more popular, people are also spending more on arcades. Maybe that happens. Maybe not though. A great spurious example is this idea that the number of non-commercial space launches tracks really nicely with the number of sociology doctorates given out in the country. There's probably nothing there that leads to one or the other. And then, again, from an education perspective, the amount of mozzarella cheese people consume tracks nicely with how many civil engineering degrees there are. And this webpage has a whole bunch of other ones. Unfortunately, most of them are, the ones that got highlighted the most are about people dying and that kind of stuff. It's not as fun as these ones. So, but if you're interested in more, they're definitely there. So we see this all the time, though. If we collect too many things, we're just by pure random chance going to find things that look like they're correlated with each other, but in fact, there's no actual relationship there. And this comes back to the issue, the question before about correlation versus causation. Most of these models are only learning correlations between attributes and the outcome, and not necessarily that the attributes cause the outcome in the first place. So we want to be able to figure these things out. Okay. So the key thing being we have a data set with lots of attributes, lots of columns. We want to remove ones that don't help us in our prediction. We'll avoid some spurious correlations, we'll avoid running too long, etc. Two classic ways of doing this, and this came from statistics originally, so maybe some people have seen this before, is the idea of forward search and backward search. The forward search says, let's just find the attribute that best predicts the label, the outcome. We're going to start with just that one. So train a machine learning model that has just a single attribute inside of it. Then consider all possible pairs that include that first best one. So if age was our best predictor, now include each of the others with age and see which combination is best. And if that is better than age alone, keep going. Next test the best triple, then the best four attributes, etc. And we continue until it's not helping our performance anymore. So we're not getting a more accurate prediction by adding in attributes. So this is a bottom-up approach. Start small with only only one attribute, and consider more and more as you go along. The opposite of bottom-up is top-down. So we can start the other direction. We can remove one, and then see how that does compared to using all of them. So first remove the age, see if that's as good as all of them together. Then remove education, etc. And if removing one is better than having all of them, keep going. Next, remove 2, and then remove 3. Always remembering which ones you removed previously. Again, we'll continue until there's no gain in improvement. So these are very heuristic methods for doing this. They're not necessarily looking at the data, they're just looking at performance on the data. But that fits with our whole trying to do better on a task model. Question?
Is heteroscedasticity an issue to consider, especially with large data sets?
A really good question, and one that I'm not sure I have a good answer for at the moment. Sending an email, I could come back to that one too. Possible problems with these forward and backward methods, though, is that they're greedy. So the idea being there that whatever decision they make at the beginning persists forever. So in the forward method, if one attribute is deemed to be the best alone, then all other combinations it finds includes that one. And it could be the case that the best pair doesn't necessarily include the best singleton. And likewise for backwards, once it removes one, it stays removed forever. And so these aren't guaranteed to be optimal. We can maybe show that they're within some percentage of optimal, but they're not going to give you necessarily the best combination always. They're fast to run, but we trade that off with not necessarily finding the best. Additional methods we might use instead. So there's univariate feature selection. This is similar to how we do the first step of forward search. We do a bunch of statistical tests to see how relevant each attribute is to the label. So maybe a chi-squared test or correlations or other things there to find the ones that are most predictive and then save the best ones. So I would rank all of the different attributes and then maybe take the best 10 or the best 10% or something. Question?
This question is, how does Bayes searches fit in within forward/backward search? They said they weren't really familiar with Bayes search, but have just heard of it.
Sure. So search in general is the problem of trying to find what the best combination of something is. And so I'm not quite sure what Bayes search is in this context. Usually with, if it was Bayesian, then we might have some prior probabilities over all these things, then it would be searching and updating that as we go along, but I'm not quite sure. Okay. Another way to do this would be principal component analysis. How many people have used PCA before or heard about it? Yeah, a good amount of people. So again, from statistics, the idea that instead of looking at the original attributes, let's figure out how much come up with different explanations of the variance, then include little bits and pieces of all the different attributes, and then we're going to use that instead. So if we do PCA, we're going to find that, okay, most of the variance is explained by this combination of the attributes. And what we'll do is we'll actually make a new attribute that is that linear combination. So it's going to have a set of weights for each attribute. We're going to multiply those, get a new value, and that becomes a new attribute that then replaces the others. And then we can keep around the second, the third, the fourth best, depending on how many are useful. So this actually changes which attributes we're looking at as opposed to simply removing some or keeping some around. A little bit different way of doing it. These are all sort of popular ways of doing this. And in R and Python both have plenty of examples of these. Scikit-learn will be the machine learning library we use in Python. You can look up the API and it has some different examples of these things. In our code example for today, we're just going to assume that we know the best variables ahead of time. We've whittled that down to 7, but you could be running these methods to figure out which ones are most relevant. So we're not going to do it in the code, but I wanted people to know that this is the kind of thing we look at. Okay. Questions about feature selection? Okay, hopefully we can go through this one pretty quick because we've talked about it a couple times already. This idea of splitting the data sets. So, and in fact, let's just, we've already talked about this. People brought up these issues as we've gone along. So it turns out that if we have a data set ahead of time, it can serve multiple purposes for us. So we could be using it in different ways as part of the learning process. So people have mentioned that it could be used for learning. So this is what we're training the model with. It can be used for evaluating how well it's doing. And I even heard somebody mention validation before. So what do all these things mean? If we think about all of our available data being at the bottom, each instance inside of there could play one of three roles in learning for us. So we're going to take most of our data and put it in what's called a training set. And this is going to be the data that we actually give to the machine learning algorithm to learn a model for us. So this is the instances that we learn from. We don't use all of them because, again, we don't want to memorize things. But we're going to learn from most of it because the more information we have available to learn from, the better we can learn. So this data tells us what patterns we should be finding in learning. We might split off the remaining stuff into a validation set. The idea here is that while we're learning, this keeps track of how we're doing. So we don't wait to the end of learning to see how are we doing, but we monitor our progress over time. Especially important for neural network methods because they're going to keep looking at the training set over and over and over and over. This tells us when we can stop looking at the training set. With random forests, they're going to be one of the key hyperparameters that we'll get to in a second, being a setting of what goes into the algorithm. This is how many trees there are in our forest. We might use a validation set to help us find the right number of trees because it's part of the learning process we're deciding those things. The last thing is after we finish learning entirely, we have a test set that we use for our evaluating our performance. So the question way back before was what's the relationship between experience and performance? We save some of our experience that we then calculate our performance on. This is the part that we calculate it during training. This is the part that when we're finished. Another way of looking at this is the training and validation set combined are maybe data you have ahead of time, and then the test set predicts how well you would do in production. So this would be information I'd have about survey respondents earlier, and this would be essentially how I do when people actually take my survey. How accurate was I about whether or not they actually responded or not? But if we have the whole data set available in advance, we can split it in this way, and it sort of emulates the production aspect of it. Just comparing these, the training versus validation set, we don't want to memorize things, so we keep some of our training data for validation that estimates our generalization during training. Validation versus test set. The validation set we evaluate during training. The test set we evaluate when we're done. So this one is supposed to approximate how we do over here. Questions about the three types? Okay. So one important note is that before we assign instances to any one of these three, we randomize the order of the instances. We don't want any order effects, because you can think about sometimes when we collect our data sets, maybe like the earliest respondents are first, and the later ones are at the bottom. And so we don't want those effects to matter in here. Basically, we're doing a simple random sample of our data to build our training set in the first place. So all the benefits we get of simple random samples in population studies, we also get in machine learning. There's two different ways of splitting once we've randomized. When we build that training, validation, and test sets, we could either pick a certain percentage. So maybe I pick 60% of my data to be training, 20% to be validation, and 20% for testing. Is one way. The other way is k-fold cross-validation. Talk about that, and then we'll take our next break. Okay. So how many people have heard of k-fold cross-validation before? Few, but not everybody? Okay, good. The idea here is that we want to take all of our data and split it up into k equally sized pieces. So instead of worrying about training, validation, and test sets, I'm just going to take and split this whole thing into 5 pieces. K here is 5. And what I'm going to do is I'm going to train multiple models. I'm going to first say that the first fold is my validation, the second fold is my test, and the remainder is training. Then I'm going to repeat, shifting everything over by 1. Now the second fold is validation, the third fold is test, and the rest is training. And I repeat until every fold has had an opportunity to be each type. The benefit of this approach over saying that 20% of my data is test is that I can aggregate my results across all the different folds so that I've got a bigger N for my evaluation set, And so I've got a little bit more power in my statistical test. The downside, of course, is that all of these models are correlated to each other because like this block of training is used here, here. In fact, I think the last one. It's used here, here, and in all the other models except this one. And so there's some issues with the models being correlated. So it's not a perfect statistical test at the end, but it gives us a little bit more power if we have smaller data sets. The smaller your data set, the more likely we are to maybe use this method, so we get a big N for our evaluation. If we have tons of data in the first place, maybe we're okay just using the method of saying this amount is our training data, and this amount's our testing. Question?
How many folds should I choose? Is there research on that?
That is a good question. Some of it is data set dependent. Common settings are 3, 5, and 10. At least 3 if you're going to include a validation set so that you've got enough for all of them. But 5 and 10 tend to work pretty well in practice. In the extreme, you can do k equal to n, the entire size of your data set, and that's called leave one out cross-validation, where you train on everything and then make a prediction. I personally am not a huge fan of that just because it's assuming you have more training data than you probably would in the real world, but it has its uses too. Question?
All right, so this is, the purpose of this is just to get a nice performance.
Mm-hmm.
Now what about my final model? I want to use, I get some performance estimate, now what, which is my model? Obviously, I'm not going to choose any of them, but I'm going to retrain. Am I going to retrain on the whole thing?
Great question.
On the whole, you know?
Okay, so I think I can answer that in the next slide. That was a fantastic question. Okay, so the most likely place we are to use k-fold cross-validation, aside from having small amounts of training data and needing a big N, is that we need to be able to tune the right parameters to the algorithm. So a parameter in here is the things that are being learned by the machine learning method, and we'll see some examples of that soon. We use the term hyperparameter when it's a setting for the algorithm itself. So like in a neural network that we'll see in a bit, is just a bunch of neurons connected to each other. So one thing we care about is how many neurons are we going to use? That's a hyperparameter. What learning rate should we use that decides how aggressive it's going to change its learning over time is another hyperparameter. So if we want to tune those kinds of things, that's when we tend to use k-fold cross-validation. And here, we're going to not take our test set out of here. The basic setting being we had that big pool of data before that was all of this. We're going to set aside a little bit of it for test, and then we're going to use the rest of it for k-fold cross-validation. There'll be a training and a validation part. And so what that's doing is I would have the first part's validation and the rest is training. All of this only happens during the training step. And so I would, again, do k-fold and get a performance measure for one model. Say I use 3 trees in my random forest. A random forest is just multiple trees combined together. And so if I want to test 3 versus 5 versus 10, then I would do this and see how good is 3, how good is 5, how good is 10. And then when I'm done with that, in answer to your question, once I pick the best one, then I repeat all of this using the whole thing as training data and learn only one model. So here I might have used k-fold to learn 5 different models with 3 trees, 5 different models with 5 trees, 5 different models with 10. Once I know the right number of trees to use, I say I don't need a validation set anymore. I'm going to use all of this for training and learn one total model that way. Other questions? In my research, I mostly don't use the k-fold stuff. I just say that 60% of my data is training, 20% validation, 20% tests, but they all have their different purposes. Let's take another break, and then we're going to dive into the meat and potatoes of today, actual machine learning methods. What is a decision tree? How does it work? What is random forests? And what is neural networks?